Now that we've looked at the vapor pressure, we're going to use that vapor pressure to help us understand more about boiling points and the boiling points of liquids. The next physical property to look at for liquids is boiling point. The boiling point is the temperature at which the vapor pressure of a liquid is equal to the external pressure. Well, that's the definition, but it may not be totally clear what's happening here. How is that different from evaporation, and what are some other differences that we see? Let's look into this more closely. Since the boiling point is dependent upon the vapor pressure, we're going to only compare those two factors that really affect the vapor pressure. And those two factors were the strength of the forces, the bonds that are holding them together, and the temperature. The boiling point does change dependent upon the strength of the interactions. So you might not be surprised to know that alcohol, which boils at 78 degrees Celsius, has weaker interactions than water, which boils at 100 degrees Celsius. The stronger the interactions, the higher the temperature is of the boiling point. And that's because it takes more energy to break the bonds of water than it does the bonds of alcohol, because they're stronger bonds. So it takes more energy to get the vapor pressure equal to that external pressure. Now let's look at the effect of temperature. Temperature does affect the vapor pressure of a liquid, but it doesn't change the boiling point, because the boiling point is a specific temperature where the vapor pressure is equal to the external pressure. So we can't change the temperature to change the boiling point. The boiling point is determined, and it tells you what that temperature is where boiling will occur. But one important factor that does change the boiling point is the external pressure. If I have more pressure pushing down, that's going to mean it takes more energy to get that vapor pressure up to be equal to it. If I have less pressure pushing down, it takes less energy, and that means that the temperature will be lower. Let's look at that in more detail. Since the boiling point depends upon both the temperature and the external pressure, we must look at those two factors together. Let's imagine this system where there's three pressures pushing down, and we have one pressure pushing up from this container. While this is cool, we're going to see only one pressure. How do we make it so that instead of just one pressure up, we now have three pressures pushing up? How do we make more of the liquid vaporize? Well, hopefully you thought of it, and you thought that you should add heat. So let's do that. Now we've added heat so that the vapor pressure is equal to the external pressure. So we know that by raising the temperature, we've increased the vapor pressure of the liquid. That's our first process. Now let's change the external pressure. So right now I've got three arrows pointing down. That's my external pressure. I'm going to make this one with just two pointing down, and I'm going to make this one with five pointing down so that we can see the variation. So with the three, we needed to add heat in order to get to the right vapor pressure. Which of these three, A, B, or C, do you think needs more heat? And which one do you think needs less heat? Pause the video while you think about it. Of course, you can see the vapor pressure for B should be the same as we originally checked for it. So that amount of heat will be fine. It gets to three arrows up, and we see that the vapor pressure is equal to the external pressure. It is harder to get C to that temperature. So letter C, because it has more arrows pointing down, means that it has to have more arrows pointing up. The vapor pressure has to be higher, so we have to add additional heat. That means that the boiling point will be at a higher temperature. And for A, we have only two arrows pointing down, so we have to add less heat. The temperature needs to be lower for A. Where does this come into play in real life? Well, there's a couple of things that we can see. First off is like a mountain. So if we draw this like a mountain, you can see that letter B would be something like sea level, where we live. And letter A would be the top of a mountain, maybe something like Mount Whitney. And letter C would be the very bottom of a mountain, maybe below sea level even, something like Death Valley. How do I know that the pressure varies at different heights? Well, we need to know what atmospheric pressure means. So when we talk about atmospheric pressure, how much atmosphere, how much air is pushing downward? So when you're at the top of a mountain, there's less air pushing down. And of course, if we're below sea level, we have more air pushing down. Obviously, it's not going to be looking like these arrows and whole numbers, but it does give you some concept that as you go down the mountain, there's more and more atmosphere pushing down on you, so that we increase the external pressure on this liquid. You may have noticed this when you go up the mountains and you see that your water bottle gets larger or your bag of chips gets larger, and what's happening is there's less atmospheric pressure squeezing down on those, so that the bag of chips appears to be expanding, or the bottle of water appears to be expanding, and that's just because there's nothing pushing in and the pressure on the insides of the bags are still the same, and so it expands outward. In our case, we're going to see that that changes the boiling point. So which one has the highest boiling point? A, B, or C? Well, C should have your highest boiling point and A should have your lowest boiling point. The liquid is the same thing. It's the same chemical, but we get various boiling points dependent upon the external pressure. And so we can see for the general trend here that increasing the external pressure will increase the boiling point of a liquid. You may have seen high elevation cooking directions on the backs of some packaging. So I'm going to talk a little bit about how elevation can affect your cooking. We're going to start with boiling. Up until now, we've said that the boiling point of water is 100 degrees Celsius. Well, that's true at sea level, but we see that at different elevations, we get different temperatures. It's generally known that for about every 500-foot increase in elevation, you will see that the boiling point decreases by about half a degree Celsius. And that's because as you increase the elevation, you're decreasing the atmospheric pressure, and so the boiling point will be lowered. And of course, if your water boils at a lower temperature, things like pasta will cook slower. It will take a little longer to cook. So let's look at some different numbers. We know Arrowhead Lake is around 5,000 feet, and that means that its boiling point of water is about 95 degrees Celsius, and that means it'll take about 12 minutes to cook a pasta that would normally take 7 minutes at sea level. If I go to Mount Baldy, it's about 10,000 feet. That means that the boiling point of water will be close to 90 degrees Celsius, and we see that it takes about 17 minutes to cook that same package of pasta. If we go to Mount Whitney, which is the highest point in the United States, continental United States, we see that it's about 14,000 feet. The boiling point of water is 86 degrees, and that means it'll take about 22 minutes for that same pasta to cook. And if we go all the way to Mount Everest at the very top, it's about 29,000 feet, which we'll say is about 30,000 feet, and that means that the boiling point is about 67 degrees Celsius, which means it'll take almost 40 minutes to take that same bit of pasta that took 7 minutes to cook at sea level will now take 40 minutes. So as you can see, the elevation affects the boiling point, which affects the length of time it takes to cook your food. You will not be asked this on the exam. I just thought it was interesting and you might be interested to know it. So we looked at how it affects the boiling, but now we can also look at how it affects baking. So baking, the bigger effect comes from the rate of evaporation. We know that high altitudes, the evaporation occurs faster. So one of the major things we need to do is seal whatever the baked food is so that it won't release so much water. So by sealing it, that means to make a coating on it. So one of the ways that we can do that is we can make it cook faster by increasing the temperature, usually about 15 to 25 degrees Fahrenheit. If you're baking over 3,500 feet, you'll tend to see that they increase the oven temperature for those altitudes. Baking time is decreased by 20 to 30% because you increased the oven temperature. In general, you need to increase the amount of flour present by 1 tablespoon at 3,500 feet and by another tablespoon per every 1,500 feet above that. So the flour helps steady the rise of the baked goods, and it adds a structure that traps those gases so they can't escape from your baked foods. In general, we're going to decrease the amount of sugar because as the liquid evaporates at these higher elevations, that means that there'll be an increase in the concentration of the sugar so that foods will taste sweeter and things will burn differently because of that sugar being present. In general, we try to increase the amount of liquids by about 1 to 2 tablespoons per 1,000 feet. And of course, this is due to the loss of liquid due to evaporation at these higher elevations with lower pressures, allowing them to evaporate faster. Again, above 3,500 feet, we tend to decrease the amount of baking soda and baking powder by about 20% at 3,500 feet, 50% at 5,000 feet, and almost 75% at 6,500 feet. And that's because those things create gas bubbles in your food. And what happens is, because the way that they're trapped, if you use too much, it starts to rise really rapidly because there's lots of gas being formed, and then it'll fall down and go flat. So we don't want that to happen, so you add less baking powder and less baking soda. Same thing for yeast. Again, for the same idea, we want it to not rise as quickly, and so that it won't go flat later on. So as you can see, there's a lot of changes that need to be made at higher elevations. So you'll often see this on the back of cake boxes and things like that. It'll tell you how to cook at the higher elevation and what to increase and decrease. And again, this cooking information is just for your interest. You won't be asked specific questions on the exam. Most other cooking techniques, such as roasting and grilling, do not use a lot of moisture, so they don't worry about the temperature of the water. And in those cases, you won't really need to change the way that you cook, except to know that in general, meats tend to dry out a little bit more, again, because the water evaporates faster. Things tend to be dried out. There's not much you can do about that for your cooking, but it does happen. In other things like eggs and things like that, which have a high water content, again, they will dry out faster. You don't want to heat them any higher. You just want them to cook a little bit longer. And finally, cooking with microwaves does change a little bit, and that's because microwave ovens heat up foods by exciting the water molecules in the food. The microwave radiation makes the water molecules move faster, and that tends to heat up the food. And that means that it may take a little bit longer to cook in the microwave, but for the most part, we don't see a huge difference in microwave cooking at high altitudes. And once again, none of the cooking information will be on your exam specifically.